All right, let's get started. So welcome and thank you for coming to the session. My name is Ashish and I am a product manager with Azure HDInsight team. And today we'll be spending next 1 hour to talk about HDInsight Interactive Query and how you can do interactive analysis on a very, very large data set that is sitting on a commodity storage system such as Azure Blob Store or Azure Data Lake Store. But before I kind of go a little bit more deeper and start talking about it, how many of you have heard of Azure HDInsight? Okay. How many of you have actually built a cluster? A few of you. And how many of you have done a production deployment? A few of you. Great. Excellent. So if we think about the interactive pipeline, and I think if you're working in a BI space and working in a sort of a big data space, this is the usual architecture that you usually kind of come across. So for example, you ingest data from various different data sources, and then transform the data. You need to clean the data, prep the data, and transform it. And then depending upon what engine are you using to work with this data, so for example, if you are using Hive, for example, then you'll convert that data into ORC file format, which is the optimized file format to work with Hive. And if you are using, let's say, Spark, then you will convert that data into the Parquet file format, which is an optimized file format for Spark to give you great speed. In some cases, you would also load that data into a data warehouse or a relational store. Maybe you have a Teradata-based system, Netezza-based system, or maybe the Oracle or a SQL. And once your data sort of lands in there, and then you start serving this data to your BI analyst, maybe data scientist, and so on and so forth. But one of the challenges that we are seeing with the explosion of this big data and data growth. So right now, if you think about how much total data is there, how much data we are producing on this planet, it's about 30 zettabyte. And by 2025, it is going to be 163 zettabyte. And so this is sort of an amazing amount of data, that's getting produced. And we see the implication of those into our pipelines as well, because we are now ingesting more data than before. We need to transform more data than we ever did. We need to convert more data into these optimized file formats than we ever needed to do in the past. And then loading into a store is also becoming problematic. Now, if you think about this problem from the perspective of you are getting, let's say, anywhere between 10 to 100 terabyte of new data every single day in your systems. How are you going to be able to transform all of that data? How are you going to be able to convert all of data into one of these optimized file formats? Just to give you some example, I was converting a 100 terabyte data set from CSV data to ORC data set. It took me 3 days and a 60-node cluster to do that conversion. And imagine you have to do that on a kind of a daily basis. You just kind of cannot kind of keep it. And so what's kind of happening with a lot of our customers is that these processes are taking more and more time than they used to take yesterday or a day before yesterday or a year before that. And so the BI analyst, who is now getting that final prepped, clean, nice data, is getting it, either not getting all of the data or getting that very, very late. And so they are actually working on really stale data. And so if you understand the value of the data, it's most useful the minute it gets produced, right? So somebody made a credit card transaction, it's very valuable data. But a week from now, it does have some value, but is it like really that valuable? I think the question that everybody got to ask. And so the session is all about, how can I interactively analyze the big data stored in a cloud storage without kind of doing all of those steps that, that we kind of talk about. Now, do you need to do those steps for some part of your data? Absolutely, yes. I think the point that we are making is that when you are receiving that 100 terabyte every single day, how do you kind of think about that? But before we kind of talk about that, just from an agenda perspective, we're going to talk about Azure HDInsight, some of the key scenarios that our customer use HDInsight for. We're going to talk a little bit more about some architecture patterns with respect to data processing and data serving. We're going to go deep into interactive query. We're going to see some benchmarks. So we're going to kind of run some very complex queries and show you the results, and also talk about some benchmark. Security is very important in any enterprise scenario, and so we're going to kind of talk about the security and then kind of monitoring of the solution. So while I talk about this, I think we're going to have a few break in between. If you guys want to ask questions, you can come up to the mic and ask questions so that other people also hear what your question is. So for those who do not know what Azure HDInsight is, it's a sort of a managed Hadoop and Spark cluster service in Azure. What we provide is what we call workload optimized clusters. So one of the challenges that we have seen with the traditional sort of a Hadoop and Spark world is that there is a lot of customization is needed in order to make something run well or something very, very performant. In a normal Hadoop cluster, there are about 100 different configuration files, and each configuration file has about 100 flags. So in total, about 7,000 different configuration. And our customers on premises grapple with which setting and what to change and what not to change. Because as a service, we run tens and thousands of these clusters on every single hour. We sort of learn from all these customer patterns and usage, and so we bring all of those knowledge in terms of these workload optimized clusters, so that the moment somebody create these clusters, they are highly optimized and ready to go. We even recommend our customers is that our best configuration is our default configuration. If you change those configuration there, then you'll be deviating from a very highly tuned system. And so do it, you are allowed to do it, but then know the implication of that. The other aspect that we do, which is very unique and differentiated, is around what we call monitoring and healing service. So we monitor every cluster that run within our service. And when we say monitor, we not only monitor the infrastructure component of it, such as the storage maybe, or the virtual machines, or the meta stores, for example, or the network. Of course, we are a cloud service, we got to do that. But we also monitor the open source services those are running within that cluster. So think about a scenario where you might be running Yarn and Hive, for example. So we keep checking the sort of health of Yarn and Hive and Hive Server Interactive. And then if there is a problem that happened with some of these foundational components, we built a service in the background, and we call it Sibyl. And so this keep kind of and it's kind of a repair service. So when we see there is an issue and it's a known issue, then healing service just go ahead and kind of patch that cluster or fix those issues. We won't be able to fix all of the issues. So in some cases, when we are not able to fix those issues, then the healing service will just create a support ticket and route it to our on-call. And so this is kind of a very unique in this space if you think about it. We have a lot of focus on productivity, and so I'll show you some of the tools. If you think about the various different personas, those are involved in the data chain, all the way from the data developer, who's maybe writing that Spark job or a Hive query, all the way to a BI analyst who might be consuming this data, or a data scientist who might be consuming this data via Jupyter or Zeppelin. We kind of work very hard to make sure that they are productive, and all of these tools sort of work. Enterprise-grade compliance, security, and SLAs. Again, we are an enterprise service, and so our enterprise customers keep us awake and make sure that we are making advances there, and so we're going to kind of talk about that. We have a curated big data marketplace. Again, if you think about this space, it's a very nuanced space. Every customer kind of has a slightly different needs, and thereby there is a great desire to bring their own tools, for example, or their own solutions that they kind of want to bring on top of HDInsight. And so we have built this curated big data marketplace where we work very closely with some of our partners, and our customers can then very easily provision these applications on top of HDInsight and take advantage of those. We have a per minute billing model with no special services and support contract required. Again, if you know open source is free, right? You can go to the GitHub and download all of the open source you want, and that's how the business model works. The way people kind of make money in this business is at the back end of it by selling the support services or the consulting services and whatnot. In the case of HDInsight, we thought, that is a kind of a big problem, and we need to solve that. So there are no special support required, not only for the sort of Azure bits, but also for the open source bits. So we provide support on entire stack. So if you've not seen this before, you could do all of this with ARM template or a CLI or a PowerShell. So go to the data and analytics, click on sort of a cluster type. And so we have a Hadoop, HBase, Storm, Spark, R Server, Kafka, and then interactive query that we're going to talk about today. Then if you want multi-user access and role-based control for your cluster, we have something called Enterprise Security Package. And so this basically provision Ranger as part of your cluster creation. And so you can basically define your policies, and we'll talk about that. Now, one of the important aspects of HDInsight is that we do not use HDFS. We basically rely upon the cloud storage system, such as Azure Data Lake Store or Azure Blob Storage for the storage needs. We do have a sort of a local HDFS that is there in the cluster, but that's typically only used for keeping the intermediate job results and things of that nature. We do not recommend using that. So these storage systems are really, really great in a sense that they're proven at a cloud scale. A lot of time we hear complaint from our customers that on-premises, sort of managing and scaling SDFS is one of the hardest bit of this whole ecosystem. And so in the cloud, because we offload that to fully PaaS services that kind of make 3 copies of your data anyways, it gives us a great advantage. And then it also helps us do something very interesting, which is decoupling of your compute and storage. And once that happens, you can have a scenario where you have a petabyte of data sitting in a blob store, and you're really not paying a lot of price. And then you may not even have a sort of a Spark cluster or a Hive cluster or a Hadoop cluster running on top of it, which is a great agility for our customers. Then you pick up nodes in terms of what kind of a node that you need for the worker node and head node and Zookeeper in this example. And then we'll let you pick one of the marketplace application, as I talked about, for very specialized needs there. And once you do that, your cluster will be up and running. Now, once people create clusters, what do they do with it? So the key scenarios for us, one of them is ETL and batch. It's a quite classic scenario for these kind of systems. Interactive exploration, where people use Hive on LLAP, which we're going to kind of talk about today, or Spark SQL. Data science and machine learning, streaming. This is a very popular scenario. A lot of our customers sort of get data from various line of business systems or IoT systems via Event Hub or Kafka, and then they do stream processing using Storm and Spark streaming. Traditionally, our customer use Storm quite a bit, but we see a clear trend where people are favoring Spark streaming, for the streaming needs. And then once they've processed the data, they would put data into HBase for hot path analytics, or a Cosmos DB for a hot path analytics. And then for cold path, they'll just dump data into Azure Blob Store or Azure Data Lake Store for further processing. And then the last one is, and we're seeing quite a bit of this in last 1.5 years, where people already have a sort of a gigantic Hortonworks sort of Cloudera clusters, and they simply want to kind of migrate them to HDInsight. So those are, kind of a key scenarios that we see, but today's focus is going to be on an interactive exploration part of it. So, talking a little bit more, getting a little bit more deeper into this idea around elasticity of the cloud, where you can separate your compute from storage. And as I said, we do not use SDFS, so all of your data can be stored in Azure Blob Store and Azure Data Lake Store, and you're practically getting infinite amount of storage in terms of how much data you can store there. You get a very high level of bandwidth. So in the newly announced tier for Azure Blob Storage, you can get up to like a 50 gigabit per second bandwidth from one storage account. And they have a plan to go up to 100 gigabit per second by end of this year. So from a bandwidth perspective. If you are using Azure Data Lake Store, the claim is that there is no bandwidth, capacity, or IOPS limit on those stores. So they're really, really sort of a scalable system in terms of where do you store your data. In terms of the HDInsight cluster, then you can scale up and scale down this cluster. Doesn't really matter, or wipe this cluster off. Doesn't really matter because your data is in the blob store. Not only you can do that, you can do something very interesting. Interesting in a sense that you can actually bring multiple different clusters against same data and same metadata. And we see that's kind of happening quite often with our customers, in a sense that earlier there used to be one gigantic sort of a cluster, and then everybody tried to come to that one cluster. And so the workload management used to become really, really challenging. There used to be resource contentions among users. And so what's happening now is that people are creating these user-focused or a department-focused, purpose-built, smaller cluster, talking to the same data and metadata, and kind of serving that. And so there are three promises that this architecture kind of makes to you. One is compute is stateless and on demand. Storage is cheap and limitless. And network is meshed. And so when you add more node to your cluster or add more cluster to your architecture, you get more bandwidth as you kind of add more node with the underlying storage. So what kind of patterns then this kind of architecture enables? So if you think about this diagram here, especially from a data processing and data serving perspective, our customers typically separate their cluster into what we call on-demand processing cluster and then data serving cluster. All of them sort of talking to the same underlying storage and then talking to the same common metadata store. So if you think about the on-demand processing cluster, what would happen is that, let's say your pattern is that you receive data every 1 hour and then you need to process that data. So you could get that data into the Blob Store or Azure Data Lake Store. And then you can orchestrate a cluster creation, and a HDInsight cluster would be created for you. Once a cluster is up and running, then you can run any kind of a processing framework that you may want to use after that, right? So you may be running Spark, Hive, MR, Pig, doesn't really matter. Once you have processed the data and put data into, let's say, output directory or some other directory, and put metadata into the metadata store, and then you tear down the cluster. 90% of the HDInsight clusters do not see second day. So this is a very prevalent pattern that we see with our customers. Now, how do people orchestrate this piece? So from a Microsoft side, if you guys are familiar with Azure Data Factory, so a lot of our customers basically use Azure Data Factory to do this orchestration. Some customers have written their own orchestration because all of our APIs are REST-based and we provide ARM-based template. So there are few who have done it themselves. Now, this is a great thing from a cost-saving perspective, because you're not keeping your cluster up and running 24/7. You are using purpose-built, very optimized clusters. They go crunch the data and then they go away. And our customers save a lot of cost because of that. Now, the second pattern is around what we call data serving clusters. And think about this scenario. We all represent very large organizations with lots of departments and lots of personas. And what a tool liked by maybe one data scientist may not be liked by other data scientists. I like Spark. You may like Hive. Somebody else in the organization may like Presto. And so what you could do with this architecture is that bring all these different technologies against same data and metadata, and then have all these different personas sort of come to HDInsight, and you can serve them very, very well. You can independently scale these tiers. You can add sort of more clusters, more computing power. If you think about a department within your organization, is pretty big into the analytics, and they need quite a bit of it. So you give them quite a bit of it. Right? Then there is other person, a single person trying to drive some analytics. You give them a very small sort of a cluster with the technology that they kind of want. And so we kind of see it very, very well. Now, once you have this architecture, it's all about personas and how does these personas sort of interact with these systems. And so the way we kind of think about it, hey, what your BI analyst would need, what would power user would need, what data engineers would need, what data scientists would need. And so, for example, from an analyst perspective, we have invested pretty deeply into Power BI, Excel. We work with Tableau, for example, dbeaver, and I'll kind of do some demo. With Power BI, and especially the HDInsight Interactive Query that we're going to talk more about today, we have a direct query connection. So imagine you receive a new CSV file in your blob storage, and your dashboard kind of refreshes. So we'll show you that. Then for Power users, ODBC, JDBC, and Beeline connectivity. Developer productivity is very, very important for us. So we have made investments into Visual Studio Code. How many of you use Visual Studio Code? So there is a HDInsight plugin for Visual Studio Code, and so you can write like a Spark code. You can write Hive code into Visual Studio Code, and then you can kind of submit that code to the cluster. With respect to the IntelliJ, we have done very deep integration, especially with Spark, where you can actually run a Spark program in HDInsight from IntelliJ and put a breakpoint right inside your driver program and executor program, which is amazing if you think about it, some of these Spark programs and how difficult it is to kind of debug and get them right. And so this debugging support inside IntelliJ, sort of helps our some of the developers working with our platform to be more powerful. And then of course Zeppelin and Jupyter notebooks, that kind of comes with this interface. All right, so this is great, but why is the HDInsight Interactive Query? So one of the thing when I started, I talked about this problem around ingesting sort of a lot of data. Every day we are getting a lot of data, and this whole pipeline is becoming more and more expensive every single day. And serving fresh data is becoming more and more hard every day. But the second problem is around, as I said, we use cloud storage, right? We use Blob Store or Azure Data Lake Store. These are amazing, massive, scalable storage systems, but they are remote storage at the end of the day, right? So there is a latency involved. They are 20 milliseconds away from the cluster. And so the question becomes, how do you give very fast response if you have, a latency problem as well? So let's kind of, get into a demo. I hope. Let's switch to the demo mode. Can you guys see it? If it's in the back, it's probably I'll make it a little bit bigger. Can you see it now in the back? Otherwise, you are more than welcome to come in front. So this is a HDInsight Interactive Query cluster. And I keep my clusters name like do not delete because my colleagues are very conscious about the cost and they're ready to delete things. And so this cluster, if you look at it here in the worker node, it's a 4-node cluster. And then we have a 2 head node and 3 zookeeper node. We keep 2 head node for high availability needs. So let's say you're running a job and one of the node goes down, we just fall back to the second node and nothing happens to your job. Now this cluster, I actually use the Azure Blob Storage. So you can see there are a couple of storage accounts. Those are associated with this cluster. And you can actually get into the sort of a storage account and see all of your data. So data is living in like a blob store, as I'm showing you. And we have created a HDInsight cluster on top of it. Now let's kind of start from very basic. So in this case, what I want to do is that I have a very simple CSV file. This is basically data that I downloaded from Zillow.com. And that basically tells you in the cities in the United States where you're going to see the most appreciation of the real estate, right? That's what this data. This is CSV file. I kind of downloaded. Now my goal is to start interactively analyzing this data. It's a very small data set, but I just want to get the concept just to get started. And now I am in what I call like Ambari dashboard for HDInsight cluster. Now Ambari has a sort of a multiple function. One of them is cluster management and monitoring, and then it provides a bunch of tools for you to do easy things. How many of you have heard of Ambari before? Okay, cool. So what I'm gonna do, I'm gonna go to something called HiveView 2.0. It is basically an interface for you to kind of write Hive queries. But before I can write like a SQL-like queries against that data, I basically need to create a Hive table on top of it. So I'll click on this new table, select this option called Upload Table. And in this case, my data type is CSV, and first row was header. Now this data could have been in a blob store or Azure Data Lake store. And if I select that, I could have given the path in terms of where that data is. But just to make it super simple, I'm just going to kind of upload it from my local machine. And so this is the CSV file. I'm just going to open it. Now, the moment I do that, this tool is able to figure out, what are the, like if you look at it here, so there is a region name, state, forecast. It was able to extract that metadata out of that file. And then I can provide some more property. For example, I want resultant file to be saved as text, for example. And let's hit create. So what this essentially doing is that it's basically first uploading the file, putting file into the blob store, and then basically creating Hive schema on top of that. Again, it's a external table, so your metadata kind of lives in a relational store, and data lives in a blob store. So we did that, and now if I start writing something like select star from FC, because that was the table name, and just to limit and run this. All right, so now you can see that I'm able to SQL queries against some CSV data in a very, very quick fashion. Now let's say if I am a data scientist and I'm using Apache Zeppelin. Again, this is connected to the same cluster. And I can run the same queries here. Let's make it visible. Okay, I ran that, show output, yeah. So now I'm seeing this same data in Zeppelin, but then Zeppelin also provides some visual charts. And then I'm kind of exploring that data visually, and I can see that, okay, if I look at this, if I spend my money in Atlanta, I'm probably going to be more richer next year. This is a very simple use case. But then you're going to say that, hey, didn't we came here for a very large data set type problem? These are like a little Excel files or CSV files that you're showing me. So let's switch gears a little bit. Now on the same cluster that I was doing this work, I have a data set called where did it go? TPCDS_org. So this is the drive benchmark from TPCDS. You guys know the TPCDS. So TPCDS is an industry benchmark for the data warehouse type systems. There are very complex 99 queries that you kind of run against a data generated via this benchmark, and then you say, hey, how fast and how slow you are relative to anybody. And so this benchmark is actually derived from the TPCDS benchmark. And so what it has is it's kind of like a bunch of sort of different tables. For example, it basically mimics a store scenario. So you can see the call center, catalog page, and all of that. So that is the thing. And so this data, TPCDS_org, this is basically, again, all of this data is in an ORC file format in this case, and stored in a Azure Blob Store. And before this demo, what I did was I created kind of a schema on top of that data, schema on read. So the external Hive tables and store metadata into a meta store. But actual data is in the Blob Store in this case. And now I'm going to use a tool called Visual Studio Code. Again, this is the integration that I was talking about, where you can write the queries in a Visual Studio Code and submit it against the cluster. And so the query that I'm using here, and let's go against the database that I have, TPCDS_org. And so what I'm doing, I'm kind of using that database with 100 terabyte of data, and then writing a very complex query where I have a couple of aggregation and data coming from 4 different tables, and then there is a group by statement as well. So I'm just gonna kind of run this query, and now this query is being let's see what happened. Okay. So yeah, so it's kind of executing the query, and it's very nice interface because it can give you entire DAG information. So as you can see, that query took 4.57 seconds to execute. Granted, it did not scan 100 terabyte data, but if you look at the DAG, you would see that even on like a map 1, it scanned about 67 million records. So it's quite a bit of data sitting on an underlying blob store and very, very fast speed. But you would say that, didn't you say that, hey, converting into this ORC and Parquet takes a lot of time? And of course, we got a faster performance, but didn't you run this query against that optimized file format, which is ORC? So let's change this a little bit. So then, instead of going against the ORC database as part of the same cluster, I also have this database called tpcds_csv. And so the difference here is that the files now are in just a CSV file. These are just the CSV files, again 100 terabyte of them. And now I'm going to write this query against the CSV files. And these are non-optimized files. So let's run them again. It's running. So results are back in 5.4 seconds. And so that's the fundamental game changer if you think about it. It was never easy to get the good performance out of text. That's why people converted them into optimized file formats, Orc or Parquet or Evro or something like that. But if you can't get this level of interactivity with such a huge data set on just a CSV files or a JSON files and XML files, that kind of opens up the scenario where you can just directly query the raw data that's sort of sitting in a blob store in ADLS and give very, very fast performance to the people who are trying to kind of get to this data. So I just want to pause there for a moment and see if you guys have any questions.
So the files that you have, the CSV files, there were no clustering on those. They're just stored in one big blob.
Yeah. So the question is, hey, the CSV file that we saw, are they all stored in one blob, or is there any partitioning on those? No, there is a partitioning. So we did partition them by date. Yes.
How long it took to convert to ARC format?
The question is that, hey, how much time did it took you to convert all 100 terabyte of CSV data into org file format? If I remember it correctly, it took me a 16-node cluster and 3 days to do that conversion. Huh?
So for the use case of making just files in your data lake available to like a SQL interface, can you compare and contrast like Databricks and Spark SQL with LLAP?
Yeah.
Trade-offs?
Yeah, so that's a great question. And the question is that, hey, if you say that you run very fast, but you do not compare yourself with anybody else, then how do I know, right? So we have some benchmarks that we have done, and I have at the back of my slide, so we'll talk about that once we get to that.
One last question. One last question there. We have a H-based database that we load our CSV into. Can we run this query and directly do an insert into select star from kind of thing? Will that help us?
So the question is, we load your data into HBase for faster querying, and instead of a HBase, can we use interactive query for querying that data? Well, HBase is really a great product if you have a, sort of a point scan, or you're scanning the sort of a smaller amount of data, and you need those results to come back in like a millisecond range. Okay. Interactive query is, the expectation here is from few seconds to 5 minutes, right? But on a very large data set and large tables and whatnot. So again, depending upon what your expectations are, you can definitely kind of think about that. There is a question in the back.
Yeah, so let's say that I'm supposed to get my CSV file every 2 days. Do I need to combine them myself manually before I can start like querying them, or can that actually happen to be able to handle multiple CSV files?
Yeah. All right, so the question is that, hey, if I'm receiving every second day, I receive like these multiple of these CSV files, do I need to aggregate them into like one file to get this thing? No, you don't have to, but understand the Hadoop world and its problem with like small files, right? So if you have lots of small CSV files, you're going to run into performance issues. So the question is that, can I query? Of course, yes. But will I run into performance issues with lots of small files? Answer is yes, too.
Would I be able to combine them inside that system such that I can just have a query that try to combine them?
Yeah, so the question is that, can this automatically combine those files? Answer is no. You'll probably have to run some pre-aggregator process that kind of combines it. But the interactive query in itself doesn't have the native out-of-box capabilities that will combine files. All right. So I think we want to kind of get to this word where you are ingesting and serving to your user, right? That's the whole point. So what is HDInsight Interactive Query? So it is built on Hive low latency and analytical processing. Before, the name was long, live, and process. We figured out that it's very hard to sell with that name, so we changed the name to Interactive Query. And so a lot of people kind of understand it. Serves query directly from Azure Blob Store or Azure Data Lake Store. Works with text, JSON, CSV, TSV, or Parquet Avro file formats. Super fast performance with text data, which I showed you. The scalable query concurrency architecture. Now, sometime when we think about these systems, we think about in the notion where there are like one user or 5 users trying to kind of hit these systems. But if you think about the big enterprises where there may be hundreds of users, hundreds of BI analysts trying to kind of hit these systems at the same time, and then how do you think about the concurrency and how these engines sort of work from a concurrency perspective? And so we have found that in our testing, interactive query works really, really well with the higher level of concurrency. We actually published a benchmark around that as well, and I'll show you. And then from a security perspective, you can basically secure it with Apache Ranger and Active Directory, and we'll kind of talk about that a little bit more. So how does it work from an architecture perspective? So when I issued that query, when I wrote that TP-CDS query, the query went to a component called Hive Server Interactive. Hive Server Interactive has 2 functions. One of them is query planning, optimization, all of that. And then the second function it has is a security trimming. So this is the place where it will check whether you have a permission on a certain table, column, rows, and what those are. So all of that work kind of happens there. These LLAP daemons are nothing but just kind of a cluster nodes. And then they talk with underlying storage and metadata store for data and metadata operation. Now, one thing that is very interesting here is that these nodes have RAM in them, like a dynamic RAM. The demo that I was showing you used D14 V2 VM from Azure, and it has 112 gigabyte of RAM, for example. But then we also utilize the local SSD that kind of comes with the cluster. And so, for example, with a D14 V2 VM, I get about 800 gigabyte of SSD, right? That we don't charge. And so even with a 4-node cluster, I have quite a bit of a local cache pool if you think about it, right? I have over 400 gigabyte of RAM, and then I have a close to 3.2 terabyte of local SSD to work with. And so if you look at inside a daemon, LLAP daemon, there are these multiple executors that can execute the fragments and kind of either receive the data or do shuffle, things of that nature. And so it's a multi-threaded architecture if you think about it. If you compare this with like a Hive architecture, it's all serial, single-threaded. But here you have a sort of a multiple threads trying to get data. If you look inside the executor, then it has this notion around like a record reader. And then it basically, sort of plans and try to read the data. First, it will try to see if data is in the cache, metadata is in the metadata cache. If it doesn't find it, then it's going to go and kind of hit the underlying blob storage for that data. Now, one of the important aspects of this piece is this idea around intelligent cache. And so, as I said, caching tiers are your DRAM, your SSD, and then the last one is where your actual data is, that is Azure Blob Storage. Now, this caching mechanism is intelligent, and it does automatic tiering. So, for example, let's say you receive a new CSV file in the Blob store, and user issued a query. So LLAP is intelligent enough to do a lightweight file system check to see if on that container there is a date modified, or on that file if there is a date modified. If there is, then it's going to kind of load that data into the memory again. And so you are always working with the fresh data, and you are not in the business of sort of maintaining the cache. Engine does that for you, which is very remarkable if you think about it. Now, how does cache get invalidated, or how do you evict the cache? So by default, the policy is LIFO, last in first out. But the caching policy is pluggable. So if you want to kind of further extend and have your own policy, you definitely can do that. All right. So the question becomes, how fast it is. So for this test, we ran 45 TPCDS queries derived from TPCDS benchmark. The reason why we ran 45, because if you think about the engines that we looked at, was the Spark, Presto, and Interactive Query, which is LLAP there. These were the 45 queries that all of these could run without any modification. And so that was our criteria. We didn't want to modify any of these queries. And so in this case, 1 terabyte data set, and then we used 32 terabyte of 32 node cluster. If you look at there, and data in this case was sitting in Azure Blob Store. And so if we look at the results in terms of the total time for running these queries, so the first one is LLAP, which is interactive query with the text, which is 1,478 seconds. If you compare that with the Spark, for example, that was 1,503 seconds. Again, this wasn't the Databricks Spark. This is the Spark that's running within the. Those are seconds. Yes. For 45 TPCDS queries and 1 terabyte data set. And so, of course, if you think about the LLAP with the cache data, it was 1,061 seconds. That was the best. But that wasn't that was okay. We kind of knew that might be the case. But the most important aspect to us was, hey, how fast it is even with the text. It was the second best, and that was 1,478, which was the second best in this benchmark. And then just for interactive query, we ran 100 terabyte TPCDS drive benchmark, as you see there. We were able to run all the 99 queries unmodified. 41% of the queries got finished within 30 seconds, and 71% of them came back within 2 minutes. And then in this case, the cluster was like a 100 node cluster. Now, how much money did I spend to run this benchmark? In this case, it was $800 to run the 100 terabyte benchmark. All right. So the speed is great, and a lot of our customers, who are using it, are very thrilled about it. But how about the concurrency? Because again, these are not the single user systems. You're going to have multiple people in the organization and hitting these systems at the same time. And how do we think about the concurrency? So in this test, again, we ran all 99 TPCDS queries in different permutation and combinations. Our goal was to complete the workload as fast as possible, meaning that we wanted to be able to run 99 queries as fast as possible. So in a test one, we just pick one query and kind of let it run. In a test two, we ran 2 queries at a time. So first one, we ran a query, we let it finish, and then started second, right? In a second test, we said 2 queries at a time, and then we kept increasing the concurrency all the way up to test 7 where we ran 64 queries at a time. And so if you look at the results, they're very interesting. So when we run like a one query at a time in a serial fashion, it took us the longest amount of time to finish our workload. It was 1,640 seconds. And then it progressively kept coming down all the way up to where our concurrency was 32. And so region-wide was giving us like a better performance with higher concurrency, because the previous query would kind of bring data into the cache, and then new query would kind of utilize that cache. So that caching actually helped speed up quite a bit. At concurrency level 64, we started seeing a little bit of a degradation. And this is because there is a setting in the cluster where you set the max concurrency of the cluster. That was set to 32. So after 32, our queries were sort of being queued. So we do have customers who are kind of trying this in the level of like hundreds from a concurrency perspective. Now, if you think about it, hey, what if like I have like 1,000 people? Can they hit this in a concurrent fashion? Answer is probably no. These systems are not designed for that kind of a use case. In that case, people would use OLAP-based or a sort of a queue-based technology, maybe analysis services in the case of Microsoft, or Apache Druid in the case of open source, to kind of think about those thousands of users where you serve them aggregates from that perspective. But this was within the interactive query. So which one we should pick? There are three great technologies, right? Interactive query, Spark SQL, Presto. All of them kind of work really, really well. I mean, they could be a little slower and faster, depending upon who did the test, or what version that we picked. But I think the thing that we really like from interactive query perspective is this idea around intelligent cache eviction. So you're not responsible for maintaining the cache, right? The system is maintaining that cache. And then the second aspect was kind of a query concurrency, where you can run lots of different queries against same database. Now, all of these benchmarks, they are public. So we already have a blog post that talks about it. We also publish a kit so that you can generate the data and run these queries. And it's very, very simple. People can sort of set this up under 10 minutes. Of course, it will take time to generate the data, but at least you can set the test kit in 1 minute. It's on a GitHub. It's GitHub/HDInsight, and you're going to kind of see that test kit there. All right, so it's great that we could do all of this good stuff. But how about the security, right? Because again, our customers are enterprise customers, and they really want to make sure that there is no authorized access to the data, and their system should not be compromised. And so the way we think about security in HDInsight, I think at the parameter level, where you can actually put these clusters inside a virtual network with a very strict policies in terms of who can access, who can even come within that parameter. In terms of the data storage, your data sort of lives in, let's say, Azure Storage or Azure Data Lake Store. They provide you capability around encryption at rest with Microsoft managed keys, as well as the keys that you may want to bring to encrypt the data. Then we use HTTPS for for the encryption in transit. So your data is kind of very, very secure from that perspective. Now, for authentication, there are two aspects to it. One is around where does your identities live. So we have taken dependency on Azure Active Directory. That's where all of your identities live. But the challenge with that model is that if you think about all of these technologies, they understand Kerberos, whereas if you think about Azure Active Directory, it understands OAuth. So there is a component of Azure Active Directory that we leverage called Azure Active Directory Domain Services. And it's basically a sort of a 80s Active Directory server. Then you sync your users from Azure Active Directory to this Active Directory server, which then provides you with the Kerberos tickets, for example. So that's for the identity management. Now, in terms of the authorization, we use Apache Ranger. How many of you have heard of Apache Ranger? Some of you. Okay, so Apache Ranger is a policy management product. So you could define very fine-grained policies in terms of who has access to, let's say, which tables, which rows, and which columns, and I'll kind of show you the demo. So architecturally, how does this setup kind of works, right? So you may have your users on premises in your directories. You will sync those users with Azure Active Directory, then further sync them with Azure Active Directory domain services for Kerberos. And that's what HDInsight customer talk to in terms of getting those users. Then for policies, it goes to Apache Ranger, and then kind of talks to underlying data store, in this case, Azure Data Lake Store. So if we were to kind of show you something there. So I have a cluster that I already created. This is a different cluster with our enterprise security package, meaning I have the identity management as well as the policy management with Apache Ranger, as you can see right there. So if I go to the Apache Ranger, well, let's first go here and look at some of my tables. All right. So I have a few tables here, and let's say I want to see some data. So let's start from very simple query. And in this case, I'm kind of logged in as a HDI user, okay, as you can see there. And I'm executing that query. And it will bring the results back. And as you can see, I can see all of the data here, right? Now I want to go to this Apache Ranger, which is the policy administration portal, where I can specify who has access to what. And so you can go into hide policies, for example, and define policies, who has access to what data. So that's access policies. Then you can have a row level filter, which is very interesting. So if you think about it, security in a traditional sense, you would kind of create views on a table and then assign some kind of a security there. It's very neat here. You don't have to do any of that. You can have your sort of the filtering and policies applied for multiple personas on the same table. So you don't have to create views for that. Now the one that I want to show you here is a policy called masking policy. And so the policy that I've created on that Hive sample table for this user called test user 1, and if you look at the option, I want this device make column to be redacted. The device make is the kind of easy thing, but think if this was a credit card information, for example, and you don't want it, a credit card to show to a test user in this case. So I already have this set up here. Now I'm that user 1, and I'm coming from a tool called dbeaver. dbeaver is an Apache tool. You can actually query data from anything that support ODBC, JDBC, for example, right? So I kind of connected my table here, and now this test user 1, and trying to kind of read data there. And my device make should be redacted. So as you can see here, my device make is redacted because I'm just a sort of test user, and I shouldn't be able to kind of see that data. Now let's say I am another user, and for this I will go to my desktop that is sitting in Redmond. And let's say in this case, I am a Power BI user. Okay, I'm using Power BI to connect to the the interactive query that I just showed you. It's very interactive if you think about it. Like so, if I click on some of these things, very, very interactive. And none of this data is basically cached with Power BI. We are using a direct query connectivity. So the moment I'm clicking anything, the queries are actually going back to the cluster, and that's how this is being served. But you can see it's very, very fast. But the point that I was showing you from the security demo perspective, those redacted, the device make is still redacted. And so you can have multiple different personas coming to the system from whatever wonderful, beautiful tools that they like, but the security is kind of applied at the Hive server interactive level, so it doesn't really matter from where they come. They can totally come here. So I just want to pause there for a few seconds and see if there are any questions.
So, but these are just like simple select kind of queries without any joins or aggregation going on, right?
Okay. So the question is that, hey, the query that you showed you in a Power BI is like a very simple table, and you're showing that. Answer is yes. This is just a single table and just a select statement, and I'll actually show you the query in the backend in terms of how it kind of looks like. But we have a scenario where people have kind of built these dashboard using very complex queries, and then the question becomes how fast are they, right? So how interactive this really is. So again, I cheated a little bit, and I kind of clicked on these things before, so meaning data is cached in the memory, and thereby it's very, very fast. If I pick something, let's say, in this case, maybe Tennessee, okay? And you can see there's a little bit of a loading going on, okay? And so because this data is getting from like a blob store, it's taking a little bit of time. So let's give it like maybe a second more. Let's see. So any user kind of doing this query gonna see this behavior that you see right now. But anybody else after that hits on that Tennessee gonna get very fast results because the data is in memory and data is in cache.
So can this be automated?
Yeah, so that's the.
You start with running all the queries and users have the experience.
Yeah, so the question is, how do I warm up the cache and so that everybody has the good experience? So two answers there. So for now, our customers kind of look at if they understand the user patterns and what kind of queries that they would run. They would just run that query in the morning, right? Those queries in the morning, and so thereby cache is all warmed up. I think with the community, we are working in a way where we can kind of detect like a commonly used queries, for example, and then how do we kind of auto cache them, for example. But yeah, so that's the kind of a behavior that you would see now. Now it's kind of a quite still not for this one for some reason, but yeah. So now I've been kind of clicking a lot of things. So if I look at if I go to the cluster and then look at the test view where all of these queries will be recorded. So every click that I was making is recorded here, and you can see the kind of query that generated from the Power BI.
So in that map, if I want to show a certain user data for only some states, so basically applying security at the where am I doing that, and how would that affect in Power BI?
Yeah, so the question is that, hey, I want to kind of restrict user, let's say by state, right? So what you would do in that case is that in Apache Ranger, let's go here. And in Apache Ranger, look at this policy. There is something called row level filter, okay? So you can create these row level filter, and let's say that row level filter is on state. In that case, let's say state is California, and you want to kind of make sure that a certain user only see data from California, for example. So that's how you could do it. If your question is that, hey, I want to kind of restrict it based upon from where people are hitting it, I don't know if there is a kind of a good solution that I know top of my head right now. All right, and then again, HDInsight is like a 5-year-old service. We've been in production for 5 years, and we work very, very hard to remain compliant with various different compliance needs, from Azure, from various different government bodies, the compliance authorities. So how about monitoring and operations? So as I said, our best performance is with our out-of-box cluster, so we don't expect our customers to do any kind of optimizations there. We monitor and repair your clusters and services, and then we provide SLA on the entire solution. We also, from a monitoring perspective, if you think about all of these endpoints, these are actual open source endpoints. So for example, if you think about the HBase in this case, so we're going to be kind of checking the health of that component, and if there is anything bad happens or any issue happens, we just go and take a corrective action and fix it before our customers kind of even know it. And this is just one of the internal diagram that I'm showing you. So this service called Siebel. And so what you're seeing in this diagram is that there were like 250 machines or 250 clusters got impacted with some bug that got introduced in one of the newer version of Python. And so we detected it, and our automation was able to kind of fix that, and that issue went away for our customers. This is the same thing, but on a sort of a per cluster view. So we kind of have a threshold. Let's say something is down for 15 minutes, then apply the mitigation. So in that case, that threshold was hit, and mitigation was applied. A severity 4 ticket was created. It was marked as resolved, and then we have it for our sort of auditing purposes in terms of what kind of happened. Sometime this service won't be able to resolve some of these issues, so it will just mark it unresolved and give it to the on-call, for example. This is just an example of how our internal dashboard kind of looks like on a sort of a per cluster basis. Now, it's about our monitoring. We're going to monitor infrastructure. We're going to monitor the open source bits. But how are you going to kind of monitor your applications, and how are you going to monitor maybe how much cache I'm using, and do I need to add more nodes, for example, if I'm running low on anything? So there are sort of a first-party tools such as Grafana, for example, Ambari that I showed you. But we have also done integration with Azure Log Analytics. So all of the metrics and all of the data from your cluster can go to Azure Log Analytics. And then on top of that, you can do very sophisticated analytics, not only with your metrics, but also with logs from your cluster, from your application, in terms of what's happening there. And then we have built some very specialized dashboard for you to kind of go look into in terms of what's important for a specific workload and what to do there. As I said, Log Analytics is a very sophisticated tool for trying to find patterns, trying to find issues, and you can write very sophisticated queries in terms of finding issues, inside your cluster. We use a version of it ourselves. We call it internally Custo at Microsoft, and all of our DevOps engineers and our engineers kind of use this tool in order to troubleshoot our customer issues. It's great that we have now made it available to our customers, and so that they could do the same kind of a DevOps that we do on our side. Now, how do we use it? So we basically push a FluentD agent to all of the nodes. Have you heard of FluentD before? It's basically an open source agent which can collect different kind of signals. And so that's what we install on every single node. And then we also give it like what data to collect. So for example, in one of these configuration files for HBase or for LLAP, the configuration file would say, hey, collect the logs from Hive Server 2 logs, for example, or Yarn log, for example, as well as GMX metrics. So this configuration file has the definition in terms of what data needs to be collected. Once it collects the data, then the data gets ingested at the log analytics service that we were showing you. At the time of ingestion, data gets indexed, so that's very easy to search and create dashboards and whatnot. And that's what you just saw in those previous slides. So this is how this whole architecture kind of works. You can extend this architecture by, let's say if you have an application running and that's the log that you want to kind of collect from a cluster, you would just push a configuration file with a specific information to where your log is and how you want to collect it, how you want to decorate it, and then shove it out to the log analytics service. Okay, so if we build something like this, how much is this thing going to cost? So this is like a typical cost profile, 100 terabyte of data, and you are running a 6-node cluster. You are serving like 6 concurrent sessions all the time, about 1 million queries in a month, including the storage cost and HDInsight cost. That would be something like $9,345. So just to think about how should I think about it from a cost perspective. So with that, we have about 4 minutes, and I'm happy to answer any other questions that you guys might have.
Is the Apache Ranger GA?
So the question is, hey, is Apache Ranger GA? No, it's in a preview, and we plan on making it generally available in next few months.
One other question. You showed about the row filter for a user. Does it support the fallback?
So the question is that, hey, I saw that row filter. Would it support the RBAC at the storage level or at the table level?
Row level. So giving a user,
Uh-huh.
assign a role and say anybody in that role should be accessing.
Yes. So you can specify a row level filter, and then you can assign a group, and then every user that belongs to that group would kind of see that or experience that.
Would that be an Active Directory group? Sorry.
That's for sure.
Yeah, in Azure Active Directory group, that is correct. So your groups and users are synced directly from Azure Active Directory. Yeah.
And then app.
Sorry, there is a follow-up question, and I'll get back to you.
No, and thanks for answering that. One other quick follow-up is app. The user and group. Can I list the applications and say these applications can access versus other applications?
So the question is that, hey, how about the user and groups are fine, but then how about the applications? In this word, there is no concept like a service principal, for example. Even if you think about like a Hive, and we kind of authenticate them as like a Hive users. So that's what the identities are. As the space changes, as the open source changes, we'll kind of change with it, but that's not something that is there right now.
Any plans of supporting import mode in Power BI instead of directory?
Okay, so yes. So the question is that, hey, in a demo you showed me a direct query mode. Is there a plan to support import mode as well? Import mode is already there. Yeah, import mode is already there. It's just like everybody has it. That's why I showed you a more different one.
Then if using the Ranger setup for like the row level security, so does that user need access to the underlying like data lake store file? Or
Yeah, that's a great question. So again, there are 2 types of operation in the cluster, right? So one is, hey, I just want to be able to read the data. Like I want to look at the table and see the data. So that's one use case. The other use case is that I want to be able to write the data. So maybe I'm creating a table and I need access to the path where I can create those tables. So for the first use case where the security can be maintained in a Ranger itself and you're not actually touching any storage location, you're just looking at the Hive table, for example. That we send via a service principal back to the underlying storage. And so that works well. Now, if you come for an operation where you will be creating a table, we'll look into like a storage location. In that case, we will pass your user identities to the underlying storage. And if you have authorization at that layer, then you will be able to kind of do that work. Otherwise, the permissions will be denied. So you need to have access at both places. You need to have on a ranger as well as underlying data lake store level. All right, if there is no more question, thank you very much. Yeah, thanks.